Distinguished ladies and gentlemen, we are still discussing organic chemistry, and in the last video we discussed alkenes. So in this video I want to look at alkynes. Alkynes are the third member of aliphatic hydrocarbons. We have seen alkanes, we have seen alkenes, and the last one is alkynes. An alternative name to this group of compounds is acetylenes. They are called acetylenes. It is either we call them alkynes or we call them acetylenes. Now alkynes are highly unsaturated compounds. They are highly unsaturated hydrocarbons with the general molecular formula CN H2N -2. The reason why these compounds are said to be highly unsaturated is because they are lacking 4 hydrogens, unlike alkenes that are lacking only 2 hydrogens. So this is the general molecular formula CnH2n -2, where this N represents number of carbon atoms. So they are highly unsaturated. Now let's look at the alkyne family. The first member, second, third, fourth, fifth, sixth, seventh, 8th, 9th, and 10th member. Although we call this one methane, but methane does not exist, because if we calculate the molecular formula, it will be a compound that is not even possible for it to exist. So the actual first member of these compounds is ethane. Then we have propyne, we have butane, we have pentane, we have hexane, heptane, we have octane, we have nonane, and we have the last member, the 10th one, even though we still have other members, but most of the discussions will restrict them to the first 10 members. Now, why do we say methane doesn't exist? Because the general molecular formula for this compound is CnH2n -2, where this N we say is the number of carbon atoms, and these are the number of our carbon atoms. So if we take 1 for N in the first compound, meaning I have, using this formula, I have C1 H2 times 1 -2. So this will give me C1 H2 times 1 is 2, and 2 minus 2 is 0. So you see this compound doesn't exist. There's nothing like CHO. CHO is as good as carbon, and it is not regarded as a member of this compound. So the first member actually is ethane. In ethane, the number of carbon is 2. So if my N is equal to 2, so I will have C2 H2 times 2 minus 2. So this gives me C2, 2 times 2, 4 minus 2 is 2. So the first member is C2H2. Following the same formula, this one will give me C3H4, C4H6, C5H8, C6H10, C7H12, C8, H14, C9, H16, and finally C10, H18. So these are the molecular formula of the compounds in this group. Now let's see how we can draw the structure of these compounds. Because the number of hydrogen is not similar to those of alkenes, are not similar to those of alkanes. So let's see how their structure looks like. Now let's take the first member, which is C2H2. So in this compound I have 2 carbon atoms and 2 hydrogens. So 2 carbon, 2 hydrogens. So this compound will have 1 bond above representing these 2 missing hydrogens, and will have 1 bond below representing these 2 missing hydrogens. So this is the formula for ethyne: 2 carbons, 2 hydrogens. So we put triple bonds to represent the missing hydrogens. The bond above represents the 2 hydrogens above, and the bond below represents the 2 hydrogens below. If I have compound like C3H4, which is the second member, so I have 3 carbon atoms and I have 4 hydrogens. 1, 2, 3, 4. I have 4 hydrogens. So I'm missing 2 hydrogens here. I put bond here. Missing 2 here. I put bond here. So this is how these compounds look like. So they always have triple bonds to balance the compound. So let's look at how these compounds are named. How do we name them? It's very similar to the way we name alkenes. Because in alkenes we said we only consider the position of the functional group to determine the first terminal carbon. Likewise, in alkynes we consider the functional group, which is a triple bonds, to detect our first terminal carbon. For instance, if I'm given a compound like this, then I have bromine here, I have another bromine here, and let's say I have chlorine here, and I'm asked to name this compound. Okay, what I want to consider is the position of my functional group, which is a double bond. And these are my 2 terminal carbons. So which of these terminal carbons is closer to this functional group? Of course it's this one, because I don't have any business with the subsequent groups to know my first carbon. I only have a business with the functional group to know my first carbon. So this will be my first carbon, second, third, fourth, and fifth. Okay, then while naming I follow alphabet. I name them alphabetically. So the first subsequent is bromine. We have 2 bromines, one at carbon 1, the other one at carbon 4. So I have 1,4-dibromo. Then chlorine at carbon 5, 5-chloro. Then the compound has 5 carbon atoms. So this is pentyne. I put pent. Then my triple bonds, which is a functional group, is attached to carbon number 2. If I'm moving in this position, it is found in the front of carbon 2. So it is pent-2-ine. Pent-2-ine, not in, because we are talking about alkynes here. So this is the name of this compound. 1,4-dibromo 5-chloropent-2-ine. Let's look at another example. So you see they have the same method of naming as the second member of aliphatic, second group of aliphatic compounds, that is alkenes. If I have something like this, now let's say I have my triple bonds here, and I'm asked to name this compound. So you see, as we made mention in the first time we started naming organic compounds, we say anytime you have a multi-branched compound, what we are expected to consider is the longest chain. The longest chain gives us the main compound. So based on that, I suppose this is my longest chain. So this is my main compound. Okay, if this is my main compound, this becomes a substituent. This also becomes a substituent group. Let me reduce to 1 carbon here. if you look very well, from this carbon to this carbon is the longest chain because I reduced 2 carbon atoms. So this is my longest chain. But the reason why I will not consider this one to be my longest chain is because the functional group is not found within this chain. Had it been this functional group is found in this position, for instance, so I will take this to this carbon as my longest chain. Had it been this functional group is found here. But because the functional group is found on this chain, so I won't consider this. So I only consider this one because I have my functional group on this chain as my longest chain. Okay. This is my terminal carbon and this is the other terminal carbon. So my functional group is closer to this terminal carbon. So this will be my first carbon, second, third, fourth, fifth, sixth, seventh, eighth, and ninth. So this functional group is methyl, and this functional group has 3 carbons, so it is propyl. So the name of this compound is, we have methyl at carbon 5, we have propyl at carbon 3. So P and M, which one comes first alphabetically is M. So this will be 5-methyl, 3-propyl, then the compound has 9 carbons. So this is no 9. I'll say non. Then I put the position of my functional group, carbon 1, if I'm going to this direction. So it's non 1I. Non 1I. So this is how we name a multi-branched compound. We follow the longest chain, but we must make sure that the longest chain contains the functional group. We cannot take a longer chain or the longest chain and accept our functional group in a different chain. It's not possible to name it that way. Let's look at one more example. Let's say we have something like this. Then I have chlorine here. I have bromine here. Okay. If I'm asked to name this compound, it's a multi-branched compound. So my longest chain is expected to be my main compound. And if you look at it very well, this is my longest chain. This is my longest chain. But I will not consider this as my main compound. Why? Because I have a substituent attached to one of the carbons. Now because this substituent is attached to this carbon, it means I will not consider this longest chain as my main chain. Because my main chain must contain the carbon that has a substituent group. So it means this is not going to be my main compound. So my main compound will be this one. Because I have chlorine attached to one carbon in this line, I have bromine attached to this last carbon. So I will consider this one now as a substituent group, not the main compound. Okay. So this is my functional group and it is closer to this terminal carbon. So this is first, second, third, fourth, fifth. Had it been I do not have bromine here, so I will consider this chain downwards as my longest chain, and that this is expected to be my main compound. Had it been I do not have bromine here, but because of the presence of this bromine now, I must consider this as part of my main compound. This is why I take this as my longest chain. Now, we have chlorine at carbon 1, we have bromine at carbon 5. Then this is a substituent that has 1, 2, 3, 4. 4 carbon atoms. So this is butyl. It's a butyl group. So my compound will be 5-bromo, 1-chloro. Okay, this is B and this is C. So butyl should come first before chlorine. So 5 bromo, 4 butyl, 5 bromo, 4 butyl, 5 bromo, 4 butyl. Then the compound has 5 carbon atoms. Okay, I have chlorine, 1 chloro, then this is pentine, pent2ine. Yes, I'm just using this as an example to explain how we consider substituents. When we have a multi-branch compound, we must always consider our position of the substituent groups in order to name it accurately. And while naming, we must follow alphabet. We must follow alphabet. We have bromine, we have butyl, we have chlorine. Even though I'm just using this as an example, but if we are actually going to follow alphabet, I think BR shouldn't come first before BU, because alphabetically both are starting from B or with B, but the second alphabet, this is R and this is U. Okay, yes, R comes even before U in alphabet, so I'm correct. Had it been this alphabet comes after this one, so this will be my first one to name before this one, so I'm still correct. So let's look at now we made mention of geometric isomerism, where we have cis and trans configuration, and we say that particular isomerism is only restricted to alkenes. Now, why is it that alkynes do not exhibit that geometric isomerism? Because we say geometric isomerism, we are talking about having substituents either below, both below or both above the compound, or one above the other one below. Now, we might assume that this is cis configuration, but the reason why this is not cis is because this chlorine and this chlorine are not found on the functional carbons. They are not found on the carbons with the functional group, so this is not cis. Had it been one chlorine is found here, the other one is found here, this is cis. Had it been one is found here, the other is found above, this is trans. And the reason why we cannot have chlorine on this carbon is because of the triple bonds. Provided there is triple bonds, you cannot add anything to these two carbon atoms. So this is why these group of compounds do not exhibit geometric isomerism, the cis and the trans configuration. Now let's look at the physical properties. Physical properties of these compounds. Now, one of the physical property is the second member to the fourth member are also gases. 5th member to 17th are liquids. 18 and above are solids. So they are all similar to every other member. Number 2. They are slightly less dense than air. So they are slightly less denser than air. Number 3. Now the gaseous compound. Gaseous compound are soluble in water, but slightly soluble. They are only soluble even at about 60 degrees Celsius. Only if you react them with a hot water or a warm water, then they will react. But if it is a cold water, they don't even react. So they slightly react. They are slightly soluble in water when the water is at about 60 degrees Celsius. So they don't react rapidly with water like the alkenes. Then number 4 is they are soluble in organic solvents. They are soluble in organic solvents like benzene, toluene, kerosene, petrol. All these organic compounds react rapidly with this compound. So these are the physical properties. Let's look at the chemical properties. And they have a smell, yes. They are colorless. But they have choking smell. They have a choking smell. They are colorless just like the alkanes, but they have choking smell just like the alkenes. So let's look at the chemical properties of these compounds. Now, one of the chemical property is they also exhibit exothermic reaction. We have explained this, so we don't need to explain it again. Another property is they undergo polymerization reaction. I've also explained polymerization reaction. A very good example I'll give here is when these compounds react. Yes, this is ethane. When 3 compounds of ethane react as monomers, they produce C6H6, which is benzene. So polymerization of ethane produces benzene. It's a polymerization reaction. Number 3, they undergo combustion also, meaning they react with oxygen to produce carbon dioxide and water. Also, combustion is also called oxidation. They all use the same formula. The first formula we gave in alkanes is the same formula all of them use. The formula was CXHY plus X plus Y over 4 O2 to give XCO2 plus Y over 2H2O. All of them use the same oxidation formula. Alkanes, alkenes and alkynes, they all use the same formula. So they undergo combustion or oxidation. Another chemical property is they change the color of bromine water. If we can remember, while talking about bromine water in alkenes, we say alkenes decolorize bromine water, meaning they remove the color of the bromine water to make the compound colorless. But alkynes do not decolorize bromine water. They change the color of bromine water from one color to another color. But alkenes decolorize. They remove the color to make it colorless. Another chemical property is number 5. They react with potassium sulfate. Number 6. They react with silver trioxonitrate 5 and potassium tetraoxomanganese 7 and change their color. Yes, alkynes react with potassium sulfate, yes. They also react with silver trioxonitrate 5 and potassium tetraoxomanganese 7. After reacting with these compounds, they change the color of the compounds. They change the color of these compounds, just as they change the color bromine water. Another chemical property is their hybridization. The hybridization is, so they have hybridization of sp1, that is sp. Hybridization of alkanes was sp3, of alkenes was sp2, of alkynes now is sp. Their functional group is triple bonds. Functional group of alkynes is triple bonds. Of alkenes, double bond. Of alkanes, hydrogen, not single bond, hydrogen of alkanes. So we have hydrogen for alkanes, double bond for alkenes, and triple bonds for alkynes. So these are the chemical properties we need to know regarding alkynes. Now let's look at the preparation of these compounds. How do we prepare the compounds? Now one of the major preparation is by dehydrogenation. Dehydrogenation of alkanes and alkenes. Dehydrogenation of alkanes and alkenes, meaning when we remove hydrogen from these two compounds, we produce alkynes. For instance, if I have C2H6, then I remove 4 hydrogens from this, I'll produce C2H2. So when I remove 4 hydrogen, I'll produce C2H2. So this is alkane and this is alkynes. So I can produce alkyne from alkane when I remove 4 hydrogens. With alkenes, if I have C2H4, then I remove 2 hydrogens, I produce this compound. So it's when I remove 2 hydrogens from alkenes, I also produce alkynes. So this is one preparation method. Then the second one is by reaction between calcium carbide calcium carbide and water. Yes, reaction between calcium dicarbide and water will produce alkyne. Calcium dicarbide is CaC2. If I react this with water, H2O, I'll produce now if you look at this reaction very well, this is calcium dicarbide reacting with water. So what I produce is calcium hydroxide, which is slaked lime. Then I'll also produce my alkyne, C2H2. So by reaction between calcium dicarbide and water, I'll produce slaked lime and alkyne. The particular alkyne in this reaction is ethyne. So I can use this method also to prepare my compound. So lastly, let's look at the uses of the compound. Uses of alkyne. One of the first uses is they are used as fuel. They are used as fuel. They are used in gas lamp. They are used in gas cookers and other gaseous using equipments. Number 2, Now, when these compounds, when they are completely burnt in oxygen, that is when they undergo oxidation. When they are completely burnt in oxygen, they produce a hot flame. You see, when they are completely burnt in oxygen, they produce a hot flame. This hot flame is about 200 degrees Celsius at times, about 200 degrees Celsius. Now, this hot flame of about 200 degrees Celsius is used for coating metals. It's for coating metals and steel, and it is also used for welding. So you see, it is used for coating metals and steel, and it is used for welding of the metals and steel. So these are a very good function of or uses of alkynes. They are used as fuel in gas cookers, gas lamps, in lighters, and they are used for coating metals. They are used for welding metals and steel. And lastly, they are used in the production of plastics. Yes, they are also used as starting materials in the production of plastics and other plastic equipment. So these are the important uses of alkynes. So I think we'll stop here on this video. So in our next video, we continue from the aromatic hydrocarbons, because now we are done with aliphatic. We said aliphatic consists of alkenes, and alkynes, and we say when we finish these three, it's as good as we have finished aliphatic hydrocarbons, and now we are done with the three. So the next one that is left is aromatic hydrocarbon. And now if we finish aromatic hydrocarbons, then we are done with acyclic hydrocarbons. Then we move to the cyclic hydrocarbons.